Let's consider a reaction containing two reactant molecules forming one product. And the experimental data for this reaction shows that the order of reaction with respect to A and B are 1, giving us a rate expression something like this. The simplest explanation for how this reaction occurs according to collision theory would simply be that particle A bumps into particle B with enough energy and the right orientation to form particle C. And you'll notice that in this simple example, my proposed mechanism for what happens is identical to the overall reaction. Now, does my data support this proposed mechanism? Well, the single step in my mechanism requires A and B to bump into each other, and if I look in my rate expression, I can see that the rate is dependent upon both the concentration of A and B, which seems to make sense. So my mechanism here is consistent with the experimental data. And because in my proposed mechanism we have a single step with two reactant particles involved, we can describe this as bimolecular. Because there is only a single step in this mechanism, I can draw a potential energy diagram, as you may have seen before, something like this. In a one-step mechanism, I have a single activation energy that needs to be overcome before I can form my products. And note that in this example, I've assumed that it's an exothermic reaction, although that is not necessarily the case. Because there is only a single step in this mechanism, the speed at which that step happens is going to determine the rate of reaction. So, in this case, the rate determining step is the only step in my mechanism. And because my step involves two particles or two molecules, we describe it as bimolecular. Let's now have a look at a more complicated example, as you might see in the IB. Here is a reaction that contains three reactant particles or three molecules. Now, unlike the first example, the chances of three molecules colliding at the same time with enough energy and the correct orientation is very, very slim. So a simplified approach might be to consider a number of steps happening in my mechanism. So let's consider what a potential energy diagram would look like if there were two separate steps occurring for this reaction to take place. In this example, you'll notice there are two humps in my graph, because if there are two steps in the reaction mechanism, we are breaking and making bonds twice. The products formed in the first step are known as intermediates because they are then used in order to form the final products in my reaction. And because there are two steps, there are now going to be two activation energies, one for each step. Here's the activation energy for the first step, and here's the activation energy for the second step. If one of these activation energies is much greater than the other one, this is going to be the slower step in my mechanism because the activation energy is greater, so less particles will have the required energy to react, so that step is going to take longer. And we call that step the rate determining step, or the slow step, in contrast to the smaller activation energy, which is referring to a fast step. So if I'm interested in working out what affects the rate of reaction most heavily, it's always going to be the things involved in my slow step, because comparatively, the fast step is going to have very little impact on the rate. Let's now propose a two-step mechanism for the reaction in question. Step 1 involves a molecule of hydrogen and a molecule of iodine chloride. And step 2 involves one of my intermediate molecules, hydrogen iodide, bumping into another reactant molecule, iodine chloride. It's worth checking that when we add these two steps together, we end up with our overall rate equation. overall reaction equation. So let's add these two together and make sure we get our equation above. I'm going to add everything on the left of the arrows and everything on the right of the arrows and cancel out anything on both sides. Yep, that looks good. So let's now compare our experimental rate data with our mechanism and see if the experimental data supports it or not. So because my rate expression shows that rate is dependent on the concentration of H2 and ICl, I want to look and see if those two molecules are involved in one of the steps of my reaction, which they are. This must mean that step 1 is my slow step, or the rate determining step, and step 2 would be the fast step. Although I can never be 100% certain of my proposed mechanism, this experimental data does support my mechanism and indicates that if I am correct, then step 1 is my slow step and step 2 must be a fast step. Because this slow step contains two particles or two molecules, we describe it as bimolecular, and you might notice that the rate expression, which also contains just two molecules, tells us the same thing. If my rate determining step actually contained only one molecule, one particle, we would describe it as unimolecular. We've seen examples where the rate determining step contains two particles, we call that bimolecular. And if it were to contain three particles, we would call it trimolecular. And you won't see anything more than three particles in IB chemistry. Let's now summarise the key points from this video. First of all, as a chemist, we like to propose a mechanism for a given reaction. And a mechanism describes the individual steps that are taking place. We must then collect experimental data in order to identify a rate expression for that reaction. We must then ask ourselves, does the experimental data support our proposed mechanism? If it doesn't, then we would need to propose a new mechanism. If it does, then it helps us identify a rate determining step and the molecularity of my reaction. Remember that the rate determining step is also known as the slow step, and molecularity could be unimolecular, bimolecular, or trimolecular. Hopefully this video was of some help.